Hello everyone, welcome to yet another video of my telecom series where I explain 3GPP RAN specification in detail. In this video, we are going to look at physical and virtual resource block. This is the fourth and final part of my resource grid series. In part 1 of the resource grid series, we looked at what exactly is meant by a resource block and how does the bandwidth of a resource block change in accordance with the numerology. In part 2, we looked at the concept of point A. Point A is how the UE locates the exact frequency location of the resource grid. In part 3, we looked at the concept of bandwidth parts. We have built an impressive foundation over the last 3 videos. By the end of this part, you will have a complete end-to-end understanding of the 5G NR resource grid. Let us start looking at physical and virtual resource block, and let us finish strong. Before we dive into physical resource blocks and virtual resource block, let us take a moment to see how they fit into the complete hierarchy. At the top, we have the entire carrier spectrum anchored at point A. Remember, point A is the center of subcarrier 0 of common resource block 0. Below that, we have common resource block. Common resource block span the entire carrier bandwidth. They are numbered starting from 0. So there is CRB 0 and the center of subcarrier 0 of CRB 0 we have point A, and then we have CRBs spanning the entire carrier bandwidth. Then we have bandwidth part. Bandwidth part are a set of contiguous common resource blocks which belong to one individual numerology. So if you see this diagram, you'll understand that point A may or may not belong to a bandwidth part. A bandwidth part is a set of common resource blocks that the UE use for transmitting PDSCH or PUSCH. Inside a bandwidth part, we have physical resource blocks. Physical resource blocks are the common resource blocks which are inside bandwidth part, and they are numbered from 0 to n. And finally, we have virtual resource blocks. Virtual resource blocks are an abstraction of the scheduler, and it is used when assigning resources in the DCI or the downlink control information. Thus, each layer builds on the previous one. Understanding this hierarchy is the key to reading 5G resource allocation and understanding exactly which frequencies a UE is using. Now, let us look at physical resource blocks. Physical resource blocks or PRBs are simply the resource blocks within a bandwidth part. They are renumbered starting from 0 at the lowest frequency edge of that bandwidth part. The key here is local. The PRB numbering belongs to that specific bandwidth part and it does not belong to the carrier. So if let's say that a base station has configured 2 bandwidth parts in a carrier spectrum, and this bandwidth part would have PRB 0 at its own frequency location. This makes scheduling clean and simple. So when a PDCCH carries a resource assignment, it references PRB numbers within that active bandwidth part. So there is no need to reference the global common resource block numbering. This mapping back to CRBs and absolute frequencies is handled by the physical layer transparently. So if you remember the previous diagram, CRB 0 may not be always used. So it depends on the bandwidth part that the UE is allocated to. So CRB 0 may or may not belong to a bandwidth part. Thus, the bandwidth part may not start at point A. This diagram actually makes this concept much more clearer. This top row shows the full CRB grid starting from point A. So we have CRB 0 till CRB 24. So there are 25 common resource blocks in this diagram. And then point A is defined as the center of subcarrier 0 of CRB 0. So point A is also defined. Then we have this bandwidth part which starts at common resource block 0. So this bandwidth part has resource blocks from common resource block 8 till common resource block 19. Thus it has 12 physical resource blocks within this. So this CRB 8 corresponds to PRB 0. So PRB 0 is defined as the starting resource block of that particular bandwidth part. Thus, in this bandwidth part, CRB numbering starts from 8 and ends till 19, whereas PRB numbering starts from 0 till 11, corresponding to that common resource block. The number of PRBs within a bandwidth part can be defined as the number of CRBs at which the bandwidth part ends minus the start of the bandwidth part. So in this diagram we can see that point A does not belong to any bandwidth part for this allocation. Now let us take a look at virtual resource blocks. Virtual resource blocks introduce an important abstraction layer between the scheduler and the physical frequency grid. When the base station schedules a downlink transmission, the PDCCH carries a DCI which specifies the set of virtual resource blocks for the UE. From the UE's perspective, these virtual resource blocks looks exactly the same as PRBs. They have the same 12 subcarrier structure and then the same size. But the critical difference is how they map to actual physical subcarriers. So this mapping can be done in two ways. There is interleaved and non-interleaved mapping, which defines how the VRBs are mapped to the physical resource block. Let us take a look at both in detail. Non-interleaved mapping is the simpler of the two modes. The rule is straightforward here. Virtual resource block N maps directly to physical resource block N. So VRB 0 maps to PRB 0, VRB 1 maps to PRB 1, and so on and so forth. So there is no frequency spreading here. So the VRBs exactly occupy the contiguous frequencies you would normally expect. For push PUSCH, non-interleaved mapping is always used. So this is mandatory and this gives the receiver a predictable frequency structure to decode. Now for PDACH, which is the downlink, non-interleaved mapping is the default when DCI format 10 is used with resource allocation type 0. So in this mode, the resource allocation and then the virtual resource block abstraction is kind of transparent. So this mapping, this non-interleaved VRB to PRB mapping is done when the channel conditions are well known and then the scheduler is assigning the best quality frequencies to the UE. Now let us take a look at the interleaved VRB to PRB mapping. This is basically used for producing frequency diversity when the channel conditions are not known, or when some carriers or when some frequencies are affected by worse channel conditions. So in this mode, instead of directly mapping VRB N to PRB N, the VRBs are kind of distributed. So they are interleaved across the resource blocks of that particular bandwidth part. So in this diagram, you can see that, okay, VRB 0 is mapped to PRB 0, but VRB 1 is mapped to PRB 3 and VRB 2 is mapped to PRB 6 and so on and so forth. So this results in frequency diversity. So in the real radio channel, some frequencies might experience frequency selective fading. So they are temporarily attenuated due to multipath interference. So if all of the UE's data is on that frequency, then the block error rate will be quite high and then transmission might fail. So by spreading the data across the entire bandwidth part, so even if some PRBs failed, the rest of the PRBs would get through. So this dramatically improves the robustness for cell edge users and also for URLLC communication. So here is a clean comparison of both the mapping modes. So we have non-interleaved VRB to PRB mapping and an interleaved VRB to PRB mapping. So non-interleaved is best for UEs near the base station and with good channel conditions. The scheduler knows exactly which frequencies are the best and then can target them precisely, maximizing throughput. Interleaved is best for UEs at the cell edge where frequency selective fading is a problem. Spreading data across the entire bandwidth part means the transmission is even more likely to succeed under challenging conditions. For the uplink, non-interleaved mapping is always used. For uplink, interleaved mapping is never used. For the downlink, the network configures the interleaving capability via RRC, and then on per transmission basis there is a DCI which carries a single bit which is the VRB to PRB indicator to tell the UE which mapping mode has to be used. Thus this per transmission flexibility is a key component of VRB abstraction. And that's a wrap. Let us bring together everything that was covered in the whole 5G NR resource grid to one final summary. So in part 1, we looked at the concept of resource block. The fundamental unit of a 5G NR resource grid is a resource element. In 4G, a resource element is defined in both time and frequency domain. A resource element is defined as one subcarrier in frequency domain and one symbol in time domain. In 5G NR, a resource block is defined only within the frequency domain. It consists of exactly 12 subcarriers. The bandwidth of the resource block varies in accordance with the numerology. For example, numerology 0 has like 180 kHz and numerology 4 has 2.88 MHz of bandwidth per resource block. Now, how does the UE knows the position of a resource block in the entire 5G NR spectrum? This is anchored via point A. Point A is the center of subcarrier 0 of common resource block 0. Once the UE knows the position of the SS-PBCH block, which is a synchronization signal and PBCH block, it can calculate point A via the parameters offset to point A, which is signaled through SIB1, and KSSB, which is signaled through MIB. Now, once the UE knows the position of the entire resource block frequency spectrum, the UE would be allocated by the base station to a certain number of bandwidth parts. Bandwidth parts are contiguous set of common resource blocks. A UE can be configured with up to 4 bandwidth parts in uplink as well as in downlink. However, only one bandwidth part is active at a time. Bandwidth parts can be switched dynamically as well. Then in part 4, we looked at the concept of VRBs and PRBs. PRBs are the common resource blocks that are renumbered locally per bandwidth part. Then VRBs further add a scheduling abstraction. So there are two types of VRBs, VRB to PRB mapping, that is non-interleaved and interleaved. This frequency diversity helps the base station to allocate the best carriers to the UE based on channel conditions. Now, thank you so much for watching Wireless and AI. I hope to produce more series like this in the coming sessions, and if you like the video and if you found this useful, please consider subscribing, please like the video, please leave a comment, and if you would like to see any other concepts covered, please comment that below as well. Share it with your colleagues and your friends if you find this useful. Thank you very much. I'll see you in the next video. Bye bye.